I guess, did Professor Skeena say where he was going to be this week? So, just to let you guys know, it turns out that Steve, this week, is at a conference in France, you know, working very hard on computer science. So I'm here and I'm going to teach the class for him. Just before we begin, so today we're going to talk about Eulerian graphs. How many people know about Eulerian graphs? So a couple of shy hands. How many people don't know about Eulerian graphs, just so that I know how fast to go? All right, excellent. So sounds good. So let me begin with an example. So the city, I'm not even sure how to pronounce this, the city of Königsberg used to have 7 bridges. So here I've drawn the river. You see there's 7 bridges. And the locals of the city wanted to find a way to walk and visit each bridge exactly once. And let's see if we can try to do this. Suppose, for example, that we start here and we walk along this bridge. We go to this island in the center. And maybe we cross the island to the other side. Maybe we walk along this bridge here. Say travel this bridge here and then go to here. But now we're stuck. Because we want to find a way to visit each bridge exactly once and walk along all the bridges, but now we're on the wrong side of the river, and yet we still have more bridges that we have to cover. So this method doesn't work. Yeah. Oh, excellent. So these are homework assignments for me to hand back. Okay, sounds good. So at the end of class, remind me to hand these back. So this method of traveling along all the bridges doesn't work. So maybe we should try, I don't know, should we try to find another way? Does anyone see a way that we can walk along? Also, this also suggests that I should have a black pen. So we want to travel and visit all these bridges exactly once. So if we travel along here, along and up there, that doesn't work so well. So we try to find a different approach. Or does anyone see a way to do this? Yeah. Okay, so say we start, let me get some more. Suppose we start here, so southeast.
Go onto the island, head over the bridge that goes upriver.
So up here, like that.
Go south.
Uh-huh.
The first bridge, go across the land.
So now here. So now we're stuck, right? Because without loss of generality, we can take either of these 2 bridges. Now we can go here. We could take one, but now we're stuck again. We haven't visited this bridge here. So does anyone see how to do this? Well, actually, it can't be done. No matter how hard you try, The only way to do this is by getting your feet pretty wet. So now the question is, given that we know that it can't be done, because I said it can't be done, and if you spent the rest of the class trying to do it, you would probably be convinced it can't be done either. But the point is, how do we prove it? So that's the goal. The goal is to try to prove that there's no way to traverse all of these bridges exactly once and then we want to generalize. Well, it turns out that this problem was studied in 1736. And as a result of studying this problem, Euler founded graph theory as a way of showing that it can't be done. And so today we're going to travel along the same path that he took. So let me, starting from this picture here, let me see if I can define some terms. So an Euler cycle, or an Euler tour, which is also called of a graph, is a circuit that contains each edge exactly once. So that's an Euler cycle or an Euler tour. So it's a way of traversing each edge exactly once. And here, we can view these bridges as edges, and these island nodes, and these sides of the river as nodes as well. So we can view, I can draw it, but we can view this bridges and islands as 4 nodes and 7 edges. So an Euler cycle of a graph is a circuit that visits each edge exactly once, and we say that a graph is Eulerian if it actually contains an Eulerian cycle. So if we look at this graph here, let's see if we can draw an Eulerian cycle for this side here. We could travel along this edge, 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 and this edge. So now we found one of probably a whole bunch of Eulerian cycles. So it visits each edge exactly once, and then ends and starts at the same place. And if we look on this right, we can do the same thing. We could start here, 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 and here. And we start and end in the same place. So, as Steve wrote, an Eulerian graph can be drawn without lifting the pen. So this is what we want to study today, is Eulerian graphs. So by the way, those of you who were in my class last semester know that I like questions and I like talking in class, because the more that you talk, the less I have to talk. And so, if this is obvious, if people want something repeated, or if people want me to speed up or slow down, whatever you want, speak out. Okay. So actually, maybe I drew one more picture, because I'm viewing Professor Skeena supposedly at a conference, in France, having a good time, and by now this is probably what he thinks an Eulerian tour is, right? The Euler Tour Company, visiting monuments. So how can we tell whether a graph actually has an Eulerian tour or not? Is this, it seems as though this should be a very complicated thing to do. But it turns out that there's actually a very, very simple way of answering the question whether a graph has an Eulerian tour. So in particular, a connected graph contains an Eulerian tour if and only if each vertex is of even degree. It's as simple as that. Actually, let me ask, now with this review, how many people have seen this before? Or for how many people is this new? So I get the feeling that they're, looking at the number of hands that raised, there are probably about 5 people. No, seriously, for how many people have not seen this before? Okay. Okay, so this is the theorem. And now let me show you how to prove it. So we're going to prove it by showing that the following 3 statements are equivalent. So this is really beautiful. So a connected graph contains an Eulerian cycle if and only if each vertex is of even degree. And actually, before I prove it, let me apply it. When we look at this graph here, here we have the city, and now we can view each one of these islands as a node, and we can view each shore as a node. And so we see that there are 2 edges to that side of the shore. There's one edge here, 2 edges here, and 1 edge here. And now we see that this graph is not Eulerian, because here this has got degree 3, and this has got degree 3, and this node has degree 3, and this node has degree 5. So we know, so Euler's already shown that this task is impossible because the graph is not Eulerian. Okay. So how are we going to prove this? So we want to show that the following 3 statements are equivalent. First, if a graph is Eulerian, then each vertex has even degree. That's the first statement. And the second statement is that if each vertex of a connected graph is even, then the edges can be partitioned into disjoint cycles. And I'm not sure if I should explain what I mean by this now or explain what I mean by this in 30 seconds. So let me just say that right there. Let me say what the third statement is, and then we'll look at each one of the proofs. The third statement says that a connected graph whose edges can be partitioned into disjoint cycles is Eulerian. So I guess we say each vertex is even degree. If so, then we can partition these into disjoint cycles. If we can partition into disjoint cycles, it's Eulerian. So statement 1 implies statement 2, implies statement 3, implies statement 1. Okay, so now let's try to prove the first statement. So if a graph is Eulerian, then each vertex has even degree. Well, the reason why each vertex must have even degree is because we don't want to get stuck at a vertex. So we can view this statement as follows. So here's a vertex. By the way, I'm really not used to teaching with, I like to teach on chalkboard, so this is an awkward thing for me to teach with an overhead projector. So, forgive me if every other slide I lose. So here's a vertex, and suppose that this vertex had odd degree. Well, the problem is that now we could get stuck at the vertex. Because maybe we enter the vertex, and now we've used up this edge, and then we leave the vertex, now we've used up this edge. Maybe later on, we enter the vertex, and we've used up this edge, and then we leave the vertex, and we used up this edge, and then maybe once more we enter the vertex here, but now we're stuck, because there's an odd, the node has an odd degree, and now there are no more bridges or no more edges that we can use to leave the vertex. So if the graph is Eulerian, then each vertex must have even degree, or else we will end up getting stuck at a vertex. And that's what Steve wrote here. If it's Eulerian, then it's an Eulerian cycle. The cycle contains each edge, and since the number of times a vertex is entered equals the number of times that it is left, then each vertex must be even. Okay, so that's the first statement that's proved. And if there are no questions, I'll go on to the second. So the second statement says, if each vertex of a connected graph is even, then the edges can be partitioned into disjoint cycles. And maybe I should say what I mean with a picture. Let's see, I'll cross that out. Okay, so here we have a random strange graph. Let's go like that. So here we have a graph, and it turns out that this graph is Eulerian, and I've guaranteed that each vertex has even degree. And now let's try to partition it into cycles. So I'm going to do this in some arbitrary fashion. So maybe I'll say this here is some cycle 1, and then maybe this here is some second cycle, cycle 2, and now here's something which is sticking off the end, so I'll call this cycle 3, and finally we see that there's one more cycle here, and then this is cycle 4. So basically, we can add each edge to be part of one cycle. And the claim is that we can always do this with an Eulerian graph. So, I don't know, is that obvious? I mean, is this easy? Do people, like, why is this true? And sometimes it's hard to tell whether it's silent because it's so obvious that nobody wants to say, or whether, people know it already and so they don't feel like saying it. And why is it obvious that you can always break this into cycles? Half of me wants to open this sprite, but the other half of me remembers that I dropped it just before class began. And with all this complicated electronics around here, I'm not sure that I want to risk splattering it. So why can we always do this? I mean, couldn't there be a case where, we start to break this into cycles, and then we get stuck, and somehow there's some strange path there that we can't connect. We start on a path and we can't find our way back to the beginning. I mean, you know, if we start the point is that here we have a cycle here, regardless of where we start, we always end up back there. But maybe it could be that we start a path somewhere here, and then we get stuck here. I don't know. Do people understand what I'm asking? Yeah. Sure. So is this clear? The fact that, I mean, is the second statement of the proof clear? If each vertex of a connected graph is even, then the edges can be partitioned into disjoint cycles. So is that clear? So the point is that here are the cycles, and the question is, why can we always partition them? Did I pressed something here, didn't I? So I should use this high tech. That's pretty cool. So why can we always partition it into cycles? In other words, what I was doing here is I was just starting at some node, wandering around for a while, and then assuming that I got back to where I began. You know, but maybe it could be that I start to make a cycle. I start at some node, and then I walk for a while, and then I end somewhere else and I get stuck. And then I don't have a cycle because I just have a path, and now I'm stuck at this node here, and I can't go any farther. Is the question clear?
You mean to say that if the graph can be partitioned into disjoint cycles?
Right. So, like, I mean, how do we know that it always can? You know, I mean, somehow the one naive algorithm for partitioning into disjoint cycles is just starting at a node, taking a path that we haven't taken before, walk for a while until we get back where we began. And this would, in fact, partition into disjoint cycles, because we start somewhere, walk for a while, wait till we get back where we began, and now we have a cycle, and now we'll remove these edges from the graph, and then we start somewhere at some other node, walk for a while, walk along the edge till we get back where we began. Now we have another cycle, so we can remove that from the graph, and then we keep doing this until there are no more edges left in the graph. So this is an algorithm that will, in fact, find disjoint cycles, I claim. But the risk is that we start somewhere, walk for a while, but we don't get back where we began. We end up somewhere else, and we get stuck. So why? Yeah. So, and is that what you guys were going to say too?
Yeah, if you are getting down, you want to get out.
Yeah.
So there's no way you can get back on the zero.
Right.
That's the only time.
Exactly. So, whatever we do, you know, each time you remove a cycle from the graph, each node in the cycle has even degree. And so when you remove this cycle from the graph, you know, like say we decide to remove this cycle here from the graph, then the remaining edges still have even degree. And the result is that because, or the remaining nodes have even degree, and because the nodes have even degree, any node that you can enter, you can always leave. And so the only place that you can ever stop is when you get back to the node that you started at. So this is really amazing because it's so simple. And if we say this formally, this is a proof by induction on the number of cycles. So in particular, I'm trying to, what does this say? Right, okay, O. So this is an induction on the number of cycles. And the point is that, all graphs with at least one cycle can be partitioned, or all graphs with exactly one cycle can be partitioned because there's only one cycle. And then we can do this by induction by removing a cycle from the graph and getting that back to a case that we know about. So that's sort of the intuition as well as a hint at how we would make this part 2 formal.
You can use mathematical induction, or with the same, the proof is done by induction. Can you use mathematical induction?
Yeah. Basically we would use mathematical induction proof. Can you guys actually see this? I mean, is this clear in the back? Because I can barely see it. What's that? So like that. So here I'm just playing, but it's kind of fun. So if each vertex of the connected, okay, so proof by induction on the number of cycles. All graphs with at most one cycle can be partitioned. A graph without a cycle is a tree, so it has a vertex of degree 1. And therefore it's not Eulerian. Assume that each even connected graph that can have up to k minus 1 cycles extracted can be partitioned into at most k minus 1 cycles. So then for any graph of even degree with k cycles, deleting one cycle leaves a possibly disconnected graph, which must be of even degree. Each connected cycle contains at most k minus 1 cycles, so the result follows by induction. So I just sort of read this. It can be made into mathematical induction, and I just said the intuitive idea before. So that's the first statement, or the second statement proved. And now let me mention the third statement. So a connected graph whose edges can be partitioned into disjoint cycles is Eulerian. So now that we've partitioned the cycles, now that we've partitioned the graph into disjoint cycles, we want to convert the cycles into an Eulerian tour. Let's see. So here we have a graph with 4 cycles. I guess to me, one of the cycles is purple, one of them is blue, one of them is green, and one of them is black. But to you, all the cycles are kind of gray. So how would we convert this into an Eulerian tour? Well, we could start with one cycle, say this green cycle here, and add this to the Eulerian tour. But now we see when we get to this node here that some cycle sticks out over the edge like a petal. It starts and ends in the same node, so we can splice this cycle into the graph. So we could add this part of the cycle so that now the tour goes like this. And then we can do the same thing when we get to here, to this node. So now we've sort of spliced in this that part of the cycle. And now we can do the same thing with this cycle here. We can add the cycle to the graph. We'll splice in that piece into the cycle. Sorry, splice this cycle into this larger cycle. And now we see that there's one more cycle that we have to add to this graph, which is this purple thing here. And we see that it connects to the graph in two different places. So we'll pick one arbitrarily. And splice the cycle in here. So now the Eulerian cycle looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and there's the tour that we have. This isn't hard, right? This is pretty easy. I don't know, is this easy? So in some sense, that's the beauty. You know, that's the beauty of this. It is kind of fun playing with these buttons here. So that's the beauty of this, is that, you know, these are some pretty deep ideas, but they have such simple explanations that it's, when you think about it afterwards, maybe it seems as if there isn't that much there after all. So how can we make this formal? Since the graph is connected, the cycles can be ordered such that the kth cycle shares at least one vertex with the first k minus 1 cycles. And then from the tour of the first k minus 1 cycles, we simply splice in the kth. So I guess here, one of the cycles here is 1, 2, 3, 1. So 1, 2, 3, 1. One of the cycles is 2, 4, 5, 2. I don't know. Is it worth me drawing this? I mean, is it worth... You know, like drawing over this. I mean, is it worth it or not? So one of this, let me just do it really. So one of the cycles is 1 to 3, 1, and he's calling this the first cycle. But then he has the second cycle, 2, 4, 5, 2. So this is the first cycle. This is the second cycle, and we can kind of splice in the second cycle here. And then splice in a third cycle here. And basically this, what do you call it, this brace here is showing the place where you would splice in each cycle in the same way that I did in the picture that I just showed you. And this is an algorithm where if we're given the cycle covering, we can find the Eulerian tour. So I'm hoping this is clear. If it's not clear, I'm happy to do something again. So there's several reasons why this is important. You know, algorithmically, it's extremely important. You can actually use these tools even to approximate the traveling salesman problem. I don't think there's going to be time to talk about it here, but you can use this idea to approximate traveling salesman. You know, this idea is, believe it or not, related to depth-first search. And the other thing, which perhaps is equally important for you guys, is that qualifier questions often have ideas from Eulerian tours. I don't know how many of you have practiced the qualifier, but qualifier questions really like Eulerian tours, and this is because it's such a simple and beautiful idea that everybody should know. So that's a good reason, additional reason to study this for those who haven't taken the qualifier yet. Okay, so what I just described gives an algorithm for finding Eulerian tours. So Professor Skeena also gave us another algorithm. Let's see if we can see what this says. So this is called Fleury's algorithm. And an alternate algorithm to the one I described, builds up the circuit sequentially. So you start at one node, pick an edge, walk along the edge and delete it, and at each step, avoid a bridge as long as possible. So in each step, you avoid going back, to as long as possible. And so maybe I should do this example here. So we're trying to find a Eulerian tour in this graph here. And as long as we can, as long as we can avoid, did he mean as long as we can avoid 1, 3, we can finish the job? Is this what he meant, or is this a typo? Mm-hmm. So let me say this first. The reason the algorithm works is that an Eulerian graph can have no bridges. When you first cross a bridge, there's no way to get back, so we must use it last. I should say one more point, which is that if the goal is to draw the graph without lifting up the pen, then in fact we don't actually need every degree to be even. If we have 2 nodes that have odd degree, then we can still draw the graph without lifting up the pen. And here what you would do is you would start your pen at one node with odd degree, keep drawing, and then you would end at the other node with odd degree. And this can be generalized. Suppose we have a graph which has, say, m nodes with odd degree. Then how many times do we need to lift up the pen? So if there are m nodes that have odd degree, and the question is, how many times, do you have to lift up the pen to draw this graph? Does that make sense? Like, oh, okay. And what he said was, he said m over 2, and then he said m over 2 minus 1, and both of this is correct depending on what we mean by